So in this section, I'd like to talk about the physiology underlying the typical pain experience. And so here what we'll be talking about is the process of nociception. And this is the physiology of how a physical impulse, like striking your hand with a hammer, is turned into a perception of pain in the brain. And so importantly, nociception should not be equated with the experience of pain, because as we'll talk about, sometimes we experience pain even without some type of tissue injury or damage. But for the typical pain experience that arises from some type of injury, the process that leads to a pain experience is called nociception. And so we're going to look at how that works here at a relatively high level. And so I'm going to give you sort of an overview on this slide, and then we'll dive just a little bit more deeply into each step in this process. So when you, for example, hit your hand with a hammer, right, there's some sort of energy impulse that occurs there. And so, how is that turned into the perception of pain? And so the first stage is what we call transduction. And this occurs where there's nociceptors, or particular cells that sit on the surface of our skin, and they pick up this energy impulse and turn that into a neural impulse. And so this is the stage called transduction, and this is done by nociceptors, and we'll learn a little bit more about those on the next slide. Then these transmit that neural impulse via afferent or sensory neurons that are in our peripheral nervous system, as well as in our spinal cord, right? So we transmit that up our nerves, and this is a peripheral nerve here, for example, in the arm, and up to the spinal cord. And then the signal would travel up the spinal cord and then up to the brain, where we would perceive that pain. Also importantly, there is some motor reflexes that can come online even before that signal reaches the spinal cord to signal that that there's pain, that there's a mechanical injury, and this is what leads us to be able to pull our hand away from, for example, a hot flame, even before we've perceptually felt that pain in the brain. And so this is a really adaptive response to that nociception, right? So we can use this as a really quick signal to engage our peripheral nerves and to engage our muscles and to pull that arm away from harm. So that signal then travels up the spinal cord where we perceive pain in the brain, and we'll talk a little bit in more detail about how that works. Then importantly, there can also be modulation that occurs in the spinal cord, both from the top down as well as from the bottom up level, and we'll also go into more detail into that. But sort of the short version is that there are these ascending and descending pathways in the brain that can up or down regulate the experience of pain. And so the amount of signaling that's coming from those nociceptors up the spinal cord, we can exacerbate that and activate that more, or we can interfere with that and dampen that pain experience because of that. So that's the overview of how that works, and so I want to get into a little bit more detail in each step. So again, that first step is transduction, and this is when these neural impulses, when the energy impulse from the injury is turned into a neural impulse, right? And this is done by these nociceptors, and these are neurons that are capable of sensing these pain stimuli. And so they're a subset of other neurons that are capable of sensing a wide variety of sensations like light, touch, and pressure. And they're located on the surface of the body and are responsible for what we call somatic pain, right? Soma just means body, as well as on many of our internal organs, and this is what we call visceral pain. When you feel pain like in your intestines or in your stomach, things like that. And importantly, right, there's many more nociceptors on the surface of our body, and this is part of why we're more able to localize pain in that area, right? To sort of feel where that's coming from. It can be hard to identify where pain is coming from inside the body. So the nociceptors that are key in nociception, well, that is by definition the case, there are three different types. And these are the alpha beta fibers, alpha delta fibers, and C fibers. And these different types of neurons are involved in transmitting different types of pain impulses. And so specifically, these alpha beta fibers, these are really small myelinated fibers. And what that means by myelinated is, if you recall back to intro psych, some neurons have myelin sheath on them. And what this is like a fatty layer. You can see that here. All right, this is the alpha delta. These are the small myelinated fibers, right? So these are, you can see this layer of fat around the neuron, around the axon of the neuron, and this allows a signal to travel really quickly, right? It allows that signal to propagate fast and not to lose steam as it's traveling down that axon. And so signals that are sent by both alpha beta and alpha delta fibers, because they're myelinated, go faster than signals that are sent by the C fibers, which are not myelinated. So alpha delta fibers are small and myelinated, and because they're narrower as well as myelinated, they are able to send a signal very, very quickly. So they are responsible for transmitting that rapid initial a signal that comes from sharp pain, either from a mechanical injury like hitting yourself with a hammer or from a burn. Right, so this is that initial experience of sharp pain. That's you can chalk that up to your alpha delta fibers. We also have these C fibers. These are unmyelinated. You can see them here. And they're responsible for transmitting that sort of secondary or dull and aching pain that you might experience when you're like sore, your muscles are sore, or you've gotten a burn, but now it's been a while and it just continues to throb for a while after that. And the C fibers are responsible for that type of pain. Alpha beta fibers are also myelinated like the alpha delta fibers, but they're larger in diameter, so they're a bit slower. And these are responsible for transmitting information about pressure and vibration, which in some circumstances can be painful, and other circumstances may not lead to the experience of pain, where you can have good types of pressure as well. But these are responsible for those types of sensory input. So those are the three types of nociceptors here. And they're responsible for, again, translating physical input and stimuli in our environment into a neural impulse that can ultimately be interpreted by the brain. Right, so that the signal is going to travel up a peripheral nerve, up to the spinal cord, and eventually up to the brain, where it's going to reach the reticular formation and the thalamus. And the thalamus is really is really the hub of the brain, of integrating sensory input and sending it to the appropriate other areas of the brain to interpret that input. And so where it's relayed next, particularly these alpha delta fibers that are responsible for this acute sort of quick and sharp pain. So these signals are relayed to the somatosensory cortex. And if you think back to other courses you might have taken where you learned about the brain and the parts of the brain, the somatosensory cortex is the area sort of right after the prefrontal cortex that's responsible for our perception of any type of stimulus on the body, right? So that each part of the body is mapped in that area of the brain, and the more sensitive areas have a larger area of the brain that is devoted to mapping that area. So you can see sort of an image of what that looks like here, right? You've got a lot of area of the brain that's devoted to perception of the lips. Hands have a lot of space devoted to that, right? So these are very sensitive areas of the body. And so there's more space of the brain that's devoted to mapping that. Just as a fun fact and As an aside, one of the interesting things about the somatosensory cortex, right, is you can see that some parts of the body are mapped near each other that aren't really near each other physically. Particularly, you can see that over here. We've got the toes and the genitals are nearby each other. This is believed to explain, in large part, some of the fetishes around feet and toes, is that because those are closely mapped, some of those signals can get crossed, and so sometimes people really do experience activation in the genital area when their toes are stimulated. And so we can also see this in other areas, but that one is a particularly memorable example of the mapping of the brain and how that works. Sorry, the mapping of the body in the brain and how that's patterned. All right, so these signals are then, as I said, relayed up the spinal cord to the reticular formation and then the thalamus and then to the somatosensory cortex. And this is what allows us to identify where we feel that pain. If that signal doesn't get there, we're not going to know that that's pain in our arm versus in our foot. Right? So we might still have that automatic motor response because we don't need the brain for that. That occurs at the level of the peripheral nervous system, but you wouldn't have the psychological experience of having pain in that hand specifically if we don't get the signal to the somatosensory cortex. All right. One interesting thing also about this is that, right, so there's actually, you might notice on here, there's no, you don't see the brain on the somatosensory cortex. And that is indeed true. There are no nociceptors in the brain, and it's the brain itself is not mapped in the brain in the somatosensory cortex. But yet we get headaches and other kinds of pain that seem to come from the brain, right? We experience pain in those areas. So how could this occur? This is due to a really interesting phenomenon called referred pain. So referred pain occurs when when nociception occurs in an area of the body that's not particularly well mapped in the somatosensory cortex. And so this is particularly true for internal organs, right? So we have potentially pain originating from your appendix, and that could feel like pain in your back or pain in your stomach. And it can be more difficult to localize this type of pain. And this is, again, because those areas are not all that well mapped in the somatosensory cortex, and so areas that are near them can experience that pain. And in the case of headaches, even though there's no nociceptors in the brain itself, there are nociceptors around our neck and on the roof of our mouth and around some of the blood vessels in our face and around our sinuses, and those aren't as well mapped as some of the areas on our skin. And so when we're experiencing pressure or inflammation in those areas, the pain can feel like it's coming from inside our head. And so this is why we can experience headaches. In particular, the phenomenon of brain freeze, right? When you experience a headache due to eating something really cold quickly, that's actually due to activation of nociceptors on the roof of your mouth. But it feels like it's coming from up inside your head. And this is why the trick that I always use, because I experience brain freeze a lot, is you put your tongue on the roof of your mouth. Your tongue is warm, and it helps to warm that back up and calm those nociceptors more quickly and make that headache go away. So, interesting phenomenon there. Yeah, so referred pain is when pain is experienced in a part of the body other than the site where the pain stimulus originates. And so that can be the case in brain freeze, as well as times when maybe you experience pain in a part of your body that's nearby the area where it's originating, but it's just not that well mapped, and so the pain is also experienced as occurring from this nearby area. Right, and this is different than times when you might have like pain in your ankle, and that because of the muscles damaged causes pain in other places. This is more about the mapping in the brain that we're talking about here with referred pain. So now we've gone through a lot of these processes, right? We've talked about transduction, the transmission process. We're just going to sort of leave at the level we talked about, just that we're sending this signal up the peripheral nervous system to the spinal cord. We've got the motor reflex that can come online at this point to pull your hand away to prevent further damage from occurring. This is our reflexes, right? We don't even need any conscious or any brain activity to involve reflexes, right? You can just evoke these, right? This is why you can just like bang someone on the knee and get a reflex out of it. But then if it does, once that pain signal does go up the spinal cord, we have perception. This is what we just talked about here with the mapping in the somatosensory cortex via signals sent from the thalamus. And then now we're turning to talking about this modulation. And this is this is where we're really going to get into some of the theories of pain and bring on the psychological processes and how those modulate pain as well. And so we'll see we have both bottom-up processes as well as top-down signals from the brain that can regulate the experience of pain from the top down, and also ways in which stimulation from other neurons from afferent pathways or bottom-up pathways and how that can modulate pain. So this is where we want to talk about gate control theory. And if you recall from the video about Ronald Melzack, he's the one who, along with Wall, I forget his first name, but I want to say Patrick, maybe I'm just making that up, but they came up with gate control theory to try to explain the impact of psychological as well as other factors on pain, right? We said that previously people had really thought about pain as just a direct response to the extent of injury, but as we know, that's not a one-to-one relationship, and other factors are impacting that. So what's the physiological mechanism that underlies that? And they hypothesized that this is the gate, or the gate, and so therefore it's gate control theory. So again, they developed this to explain the variability of pain perception, right? Pain does not always equate with tissue damage. So the main idea in gate control theory is that there's these structures in the spinal cord, and they act as this gate, a metaphorical gate that can open and close, modulating the sensory input that the brain interprets as pain. Right, so we're talking at a high level here, right? We've got something in the spinal cord, a gate that can open and close and prevent signals from coming up, and so can impact the interpretation of pain. And also there can be signals that come down to close that gate again and block those pain signals from coming up. Right, so we can open and close that gate via both top-down and bottom-up pathways, and so this is how we can modulate the experience of pain. And again, it's physical, emotional, cognitive factors can all impact the opening and the closing of these gates. So thinking first about these ascending pathways, or the bottom-up, so ascending meaning going up, and so signals from the periphery, so other signals from stimulation of the body can open and close these gates, right? So for example, this is why we rub our injuries a lot, right? If you have like a sore spot on your body, you might rub it, and we do this intuitively, but it does work to calm these alpha delta fibers, right? The ones that are responsible for these sharp pain signals. If we rub our injuries, we activate other neurons, our alpha beta fibers, and these ones are responsible, right, for that pressure. And so this is what's happening in a massage, is those are being activated. And it turns out that when those are going up the same pathway in the peripheral nervous system in the spinal cord, they interfere with one another. And so when we rub our injuries and we activate these alpha beta fibers, they block the activation of the alpha delta fibers, and so at least for a short time we have a dampening of the activation of those, and so less of that sharp pain. So just to look at these again here, right? So the alpha delta and the C fibers, these both open the pain gate in the spinal cord, right? So both of them are pain signals themselves, and so they, their job as nociceptive neurons is to send that signal up, and so they open that gate. Whereas alpha beta fibers actually are responsible for closing that gate. When we stimulate them, they can suppress therefore the activation and the ability of alpha delta as well as C fibers activation to get up the spinal cord into the brain. So rubbing and massages can help with acute pain, like from a sting or something like that, but it can also really be beneficial for these more throbbing long-term pains, and that's why we like a massage when we have a sore back. These help to close those pathways, at least temporarily. Can also open and close this gate via descending or top-down pathways. And so this is where gait control theory incorporates these cognitive, motivational, and emotional factors that influence pain. So the term they use to refer to sort of the influence of the brain and these top-down influences on pain is they call this the gait control trigger. And this just refers to that nerve impulses can descend from the brain and influence the gating mechanism. And we're not going to go into all of the details of this because there's many different ways in which this can operate. But for example, when we're distracted and we're not paying as much attention to the source of the pain, right, that can close that gate. Right? We have less activation of certain areas in the brain and more activation in others, and that allows that gate to close, and so at least to close somewhat, and so we don't experience as much pain in those cases. This is what we're going to see we take advantage of in using virtual reality as a intervention for trying to reduce pain during really painful procedures, as we're using this as a way to help close that gate. Relaxation can work for this. For a number of reasons as well. There's some physiological mechanisms underlying that. Adrenaline rushes can also close that gate, right? That's also very adaptive, right? When our sympathetic nervous system is highly activated, we're probably under threat and we need to get away from something, and so we don't need to experience that pain now, right? That would interfere with us running or doing what we need to do to get out of that stressful situation, and so we may not feel pain initially because, again, that acts to help close that gate in the spinal cord. And so all of these can lead to a decreasing experience of pain. So also want to say we can also have top-down processes that open that gate, right? Sometimes we might be very anxious about something. Sapolsky uses the example of you find a weird mole on your body, and the stress and the rumination and worry about that can open that gate, and now we might feel every weird pain or really be really sensitive to any type of nociceptive signal in our body. And so we can also have top-down processes that open the gate as well as close it. There's other things that can modulate pain. We're not going to go into a ton of detail at this, but tuning chemicals. So once you've had an injury on the body, it releases what we call tuning chemicals, and these lower your pain threshold at the site of injury. And again, this sucks, right? This is why like a paper cut, every time you bump it, continues to hurt. But this, again, would have been adaptive, or still is adaptive, right? Because it allows us to be aware of that injury and to not bump it as much and allow it to heal. And so tuning chemicals are something else that influences pain. Neurotransmitters also play a key role in pain perception. Talked a little bit about the role of adrenaline already, but and that's what but also endorphins can regulate that as well. We call these endogenous opiates, right? Meaning that they are made by the body itself. So they operate in a similar way as when we take opioids, or very serious pain killers. We'll learn more about those in an upcoming slide. But our body also creates things that look just like this. In fact, the opioids that we design as drugs are mirrored after what our body naturally creates in order to block pain signals. And so endorphins, right, this is what comes from like a runner's high, as well as enkephalins and dynorphin are all key neurotransmitters that regulate pain. There's also pro-inflammatory cytokines, and you might remember this term from talking about stress and the immune system, and we talked a lot about inflammation as being part of the immune process. And so these pro-inflammatory cytokines are produced by the immune system when it's very active in combating what it at least thinks is a foreign agent, and these contribute to sensitizing neurons, particularly in the spinal cord. And these are really heavily implicated in chronic pain. We'll talk more about chronic illness next time, but a lot of chronic illnesses and chronic pain disorders are characterized by high levels of inflammation and these inflammatory cytokines. And so a lot of interventions are based around trying to reduce these levels. I'm going to pause there, and then we'll return in the next one to talking about theories of pain. We've already sort of introduced this, the first theory of pain being gate control theory, but I'll talk a little bit more about that, and then it's the follow-up theory, also by Ronald Melzack, neuromatrix theory. So see you in the next video.